So the next talk is by Professor Rishi Raj. So he is an associate professor in the Department of Mechanical Engineering at IIT Patna. He received his PhD from the University of Maryland, USA in 2010. He is the recipient of the prestigious Swarna Jayanti Fellowship Award by the Department of Science and Technology, Government of India in 2021. His research has been recognized with the Professor K.N. Sitharamu Medal and Prize Award by the Indian Society for Heat and Mass Transfer. His research interest includes energy, boiling, condensation, colloids and interface science, microgravity sciences, and machine learning. He is also an editor of the journal International Communications in Heat and Mass Transfer.
Uh, uh, Welcome everybody, and I would like to first thank Arvind and Professor Marco for inviting me to deliver this talk, and this gels in very well with the theme with which we started yesterday and where we are today. And I am going to talk slightly differently. I am going to talk about managing heat, thermal management, as is the theme of this workshop, by probably working at the liquid vapor interface. So mostly whatever I am going to talk about is two-phase heat transfer, and once you have two-phase heat transfer, there are liquid vapor interfaces, how we can pay attention to those interfaces to address some of the thermal management challenges that we have. And in this regard, I'll be talking about primarily boiling heat transfer enhancement for electronic cooling, but unlike most of the work that's done in the field, which is surface modification, wickability improvement, wettability improvement, I am going to focus on fluidic modification. That means if you look at this single bubble nucleation, you have this liquid vapor interface. What can we do to that interface in order to enhance my boiling heat transfer and address all of the concerns that we have? And we typically do that by adding molecular additives that all of us are familiar with. They are typically called surfactants, but now newer and newer surfactants are emerging. There are ionic liquids, and you have a lot of variety to choose from. So you can very well control the interfacial properties and behavior, and accordingly, without focusing or without relying on the surface, which is tricky to handle because there are issues of fabrication as well as fouling and degradation with time, can we do something by doing modifications at the fluid level? And this is not nanoparticles, so we are essentially primarily not modifying any significant properties of the fluid. These are molecular additives which dissolve and do not change other properties significantly. And having done that, I will show you how we can use some of this interfacial output from the interfacial science to devise something like a heat spreader, and that will go in very well with the topic that has concluded. Okay, so it's kind of a vapor chamber, but something totally different, and it's wickless. It can work on completely orientation independent conditions, so any orientation gives the same results, and it's completely filled. So it's not relying on liquid to vapor phase. The issue of selecting the ideal filling ratio, and all of we know filling ratio, optimal filling ratio also varies as you change the heat flux. So that issue is done away with, and we developed this for working on a ISRO project. So I'll give regarding the background of that. And finally, since all of us are talking about machine learning, and that's where all of us are going, so I got a lot of pressure after hearing all the talks yesterday, so I said I will also bring in some machine learning. So we are going to talk about in the second part of the talk how, if we know interfaces are important, how can we manipulate interfaces or use the knowledge that we are getting from the interfaces. And one of the important knowledge or information that you get from is the sound these bubbles emit. How can we use that to do some sort of control in thermal management applications? So this is the overview of the talk that I am going to give. And since the audience is very well aware, we are talking about thermal management, and particularly the first part, as I said, is going to be microgravity application. So we are going to talk about thermal management in space, and applications are immense. And typically the way these are done is wherever you have your heat source, there may be heat in to the evaporator section of a loop heat pipe, which are very much used in space applications. The vapor that is generated goes to the cold plate, where basically it radiates heat to the cold of the space, roughly 3 Kelvin, and the condensed liquid comes back. And this is typically what ISRO also uses, and these do the job. But the point is, as our requirements are increasing and as the heat loads are increasing, Professor Marengo just explained you can hit some of the limits, and these wicks have boiling limit. So if you really now get to applications where there are hot spots, the loads are not uniform. Wherever you have a hot spot, you can have a boiling limit. What you can do is you can basically result to dry out, and that can basically lead to device failure. So one of the approaches, design better and better loop heat pipes. Other approaches, since the overall load is still not very high, it's just some sort of non-uniformity, why not we put a heat spreader in between the source and the evaporator section of the heat pipe to address this concern. The point is, if you want to do that, it needs to be thin form factor, very high thermal conductivity, effective thermal conductivity, and just solid state spreaders do not do the job. And if you look at this chart by Professor Bar-Cohen, which is talking about heat spreader thickness, we need something of the order of a few millimeters. And if you talk about the thermal conductivity, the ones which will basically serve the purpose are pumped. While pumped is great, we know the potential, right? The issue is for many of these space-based thermal management applications, you want to minimize pumps, you want to have as much as possible passive cooling applications. So we want something which is not pumped. So some of the desired features of the spreader we are looking here is it should be passive. Obviously, it should be lightweight and thin form factor. That's always true for space-based applications. It should work in all orientation if you are going to test it on Earth gravity, which will give you the hint that it's also going to work in microgravity or zero gravity. And it should be obviously, if possible, easy to fabricate, easy to install, okay, can be retrofit in existing systems. So with that problem statement in mind, we said we are going to actually boil inside a heat pipe, and it will not be a heat pipe. We are going to call it a new device. So we are actually going to rely on the science of boiling. So now if we talk about boiling, this is how we see boiling on Earth gravity, and this is my work with flying with you guys in ESA, zero gravity, how boiling happens in zero gravity. You have smaller bubbles nucleating, coalescing, forming a big bubble because there is no force of buoyancy which wants to take these bubbles away. So only surface tension acting. So this is how you will have in Earth. All of these bubbles will coalesce and form a single bubble. The problem is, if you encounter this situation, now all of your heater is dry, you are not going to use the phase change heat transfer. All the advantages of boiling heat transfer, phase change heat transfer are gone. And that's primarily because the body force, gravity or buoyancy is gone. So we want to address this in zero gravity, in confined spaces, and have a heat spreader. That's our idea. But the first challenge I hit when I came back here was, how do we do zero gravity experiments? Now ISRO has come up with a lot of opportunities for zero gravity experiments, and as I will show you, we are also flying one of the experiments in Gaganyaan, but that time those opportunities were not available. So we said, why don't we come up with a situation which is not zero gravity, but actually worse than zero gravity. So typically whenever we have a heat source, it's always at the bottom, and cold sink is at the top, because we want to use gravity, and that's why we do boiling. But now if I invert that, I am boiling, you see this is a flattened bubble. It's not going anywhere because buoyancy is also pushing it up, and surface tension is obviously pulling it up. So it's staying on the heater. It's completely dry, similar to zero gravity. So we said that if we can show something there, that will be the proof that it will also work in zero gravity. And we started with that very simple concept, and we have a very simple setup where this is a cartridge heater covered with Teflon blocks, some thermocouples, and you do boiling here. This is upward facing, and you simply invert the whole setup under atmospheric conditions, downward facing, and we do boiling under these conditions. And we want to simply do boiling not with water, as I said. Water will simply, all the bubbles will coalesce, and you saw it will form a big bubble. So we modified the fluid by adding some additives, and these additives, particularly surfactants such as sodium dodecyl sulfate, are known for a long time. And it was said in the community, what they do, they lower the surface tension, hence you have early nucleation, okay, and early bubble departure, and that's why you have higher heat transfer coefficient. However, the CHF is compromised. So if you only want to work in low heat transfer regimes, low heat flux regimes, and you want lower temperatures, that means higher heat transfer coefficient, they are good. But really, in terms of the numbers, we are looking for from 30, 50 or 100 watts per centimeter square, they are not good at all. And we said they can be good in some scenarios, and that's what I am going to show you in this talk. And during the time we were doing this research, ionic liquid also emerged as replacement for surfactants for many other reasons, and they have a wide variety. Every day new ionic liquid is coming, so we also tried one. So let me show you what's the difference in normal earth gravity boiling for water versus surfactants. So what you will see on the right is water, exactly same conditions, saturated conditions nearly, and heat flux same. This is real time, and now we'll play it slow. Exactly same. So the difference is at first instance, and that's what literature has been saying for years, they form smaller bubbles. And people said, oh, that's because surface tension is smaller. But if you really do a scaling and calculate if the size of the, the size of the water bubble here, and do that surface tension reduction and calculate the size here, you will see, you get much smaller bubbles than what you get from your calculations. So we did a lot of research on upward facing heater, on which I am not going to talk about today, but what we showed was it's not just the reduction in surface tension. Okay, surfactants are much more than that. And what is that thing? We are very familiar with. They are a foaming agent. So this is a typical experiment all of us have played in our childhood. So if you have a soap solution, detergent solution, you blow air in it, you form a lot of bubbles. Okay, this is just water with a little amount of additive. Okay, they look like this. Or for example, if you take them in a small vial and shake it, you will get a milky solution like this. Why is it milky? Because if you really focus inside, you have a lot of bubbles. Now what's the difference between water and this? Now what you have done is, in water you have added certain molecules which are amphiphilic. That means they have a part which wants to remain in water, and they have a part which hates water. So while when they are in the bulk liquid, there is a solubility limit and they can stay there. As soon as you provide them an opportunity to go to an interface, they will go to that interface, and the overall energy will be lowered and it will be much stable. So as soon as you shake these, whether it's water or surfactant solution, you basically are churning the air, you form a lot of bubbles. With water, once you stop churning, all of these bubbles combine together to form one bubble which rises up, and there is phase separation, because that's what thermodynamics governs. But now with these solutions, actually creating more interface is a more stable solution, because these molecules are stable at the interface, and that's why we form what we call froth foam, and that's used in so many of our daily applications. So we wanted to use this. That was the primary purpose. And what was the purpose? First thing, for sure, they are forming smaller bubbles. What is the issue on a downward facing heater or in zero gravity? That you have a bigger bubble which doesn't go. So if nothing else, I can simply split that bigger bubble into smaller bubbles. That also will increase my heat transfer. But actually it did something more, and that's here. So this is with water that we saw, stable bubble. Actually it will move up from the side because you are continuously pumping in heat, but if it is in zero gravity, it will not go anywhere. And exactly same heater, same heat flux, water with a small amount of a few milligrams of these additives. You see the difference. What's happening? We don't see a big bubble. That's not interesting. That's interesting, but what is more interesting is, this is how you see them from the bottom. These bubbles are coming up against the gravity, coming down against the gravity. If you just do a force balance, buoyancy on any of these bubbles is acting up. Surface tension, because it's an inverted heater, is also pulling them up. So what's pushing them down? Because if we can push them down, we have basically kind of compensated for the gravity, and anything like this can be very useful for zero gravity applications. So what's pushing them down is very simple. So imagine a big bubble which has nucleated another bubble. Now since this is a foaming solution, these bubbles do not coalesce. Their interfaces do not come together to form a bigger bubble, and that's not a thermodynamically energy favorable process. Now in between the liquid you have another nucleation, and all of us know any bubble initially in the inertially growth regime grows very fast. So the rate of change of this diameter is much more than this, and essentially what they do is they pull all around the periphery. There are smaller nucleating bubbles. They push these bigger bubbles down, and because of that, okay, there is bubble departure, and then they grow and next set of bubbles push them down. Okay, and this happens to an extent. If you look at the diagram of what is the liquid film thickness versus the disjoining pressure, there's a limit to how far you can go, but within the time scales and the forces that we need, we showed using a very simple force calculation that you have 2 orders of magnitude higher than force than that required to cause bubble departure, so you are very safe. And with that, we got up to a bubble departure frequency of 15 to 20 hertz with surfactants, and above 30 hertz, which is what happens when we boil water under standard earth gravity conditions. And this was great. So once again, just to confirm, it's the foaming nature of these bubbles which results in this bubble departure. We got a video for you from here. So focus on this bubble. You see lot of hexagonal interfaces underneath it, and there will be new bubble nucleations, and those bubble nucleations, this is a very slow video, as soon as they are growing, they pushes this apart. So you saw that bubble contact line decreasing. So here is the contact line. Now a lot of nucleations has happened, and those bubbles are growing. This is 100 times slow video, and as they are growing, they push these bubbles away, down from the heater. So this was great. This was very interesting, because now what we are able to do is not allow dry spot formation on the heater on a downward facing configuration, which is basically adverse gravity, which never works. So here is just the typical pool boiling curve on such a downward facing environment. With water, you will reach dry out at 220 watts per centimeter square, and that too because you have bubble departure from the sides, big bubble departure, right? Because we have only heater, but still we cannot get rid of the gravity. So eventually those big bubbles will be so big that they will depart from the side. So essentially speaking, this number is practically 0. And then with surfactants, we could go up to 50, and with ionic liquid maybe up to 70-80 watts per centimeter square, and this is at a subcooling of 50, which is the key here. So the point here is, even if I am letting this bubble depart, but if saturated condition, this bubble is essentially going to go back and accumulate on the heater. So just letting it depart doesn't solve the problem. You have to, once departed, somehow get rid of that bubble, right? And that's why initially the boiling experiments you have seen, we have a subcooling of 50 degree, and we get these critical heat flux values, the values here. As you start decreasing the subcooling, essentially the trend is showing you will go to 0, which makes sense. Yes, you can have a bubble departure event, but you have to eventually, you need to have a sink for that bubble. Otherwise, once departed, it's going to traverse back up. So we said, why don't we add the sink just underneath it? And we came up with a very simple design. So here is bubble departure happening. We have the visualization. We know how far these bubbles travel up to. That's 1 or 2 millimeters. Why don't we simply add a commercially available heat sink, heat pipe based heat sink that you have shown at the bottom of this, and that will do what? That will basically provide the effective subcooling that we want, even though we are not necessarily ensuring that. And what it will do is, first thing is allow heat transfer from here to here, but secondly, if you are generating a lot of bubbles, and we have shown that through visualization, these bubbles pull each other and fill whole of this space. So your hotspot was here, but that heat due to interbubble repulsion is spread throughout maybe 20 times larger area, and that is the heat transfer spreading mechanism that we can facilitate. So we incorporated those. Here is our heat spreader, which is nothing but a copper block with a 3 millimeter gap filled with this aqueous ionic liquid or surfactant solution. There is no special fabrication. Here is the hot spot, and on the top we have added quartz heat sinks, okay, and we want to go to really high heat fluxes. If you look at this arrangement, okay, this is a favorable arrangement because hot surface is at the bottom. So we do these experiments at all three orientations. Okay, we also make it downward facing so that we can demonstrate the result, and here is the performance that you see. So what I am plotting here is the heat flux you can dissipate versus the temperature, and please note there are two regions. This is the region where boiling hasn't kicked in. So there is no advantage of this mechanism until you are in the boiling regime. So it has to happen above 100 degrees centigrade so as to speak. But once you go into the two-phase regime, we also have the baseline copper block of the same thickness. You look at the slope of this curve, okay, and that gives you the thermal conductivity, which is 400 watts per meter Kelvin roughly. But as soon as we kick in boiling, look at what happens. Almost no temperature increase because heat flux can go up to 110 watts per centimeter square, almost horizontal, okay. And that's not the only thing. If you try to visualize this, here is the heat source and copper block. If you look at the back side, you still have the hot spot with copper 3 millimeter block. Now if we do it with our heat sink device, you see that heat has been completely spread. That's one. Further, if you do a temperature measurement along this cross section, this is the temperature profile that you get with the copper block. And not only is this uniform, there is a huge drop in temperature because the spreading is so efficient. So again, doing a calculation of how much is the thermal conductivity is slightly tricky here because you can still not imagine or allow in your models isotropic thermal conductivity. So I would not like to comment on that. But if you look at the numbers, they really tell you that if 400 watts per meter Kelvin is roughly, or 384 watts per meter Kelvin is the thermal conductivity of copper, what is the thermal conductivity of this device? So this is great. Not only is this great in terms of temperature, how much drop it can give you. If you look at the transient response, whether you talk about the rise time or time constant, it's much faster because the latency has been decreased. Okay, as you have more thermal mass, you have more latency and the response is not that fast. And understand that we are measuring this on the sink side. If we really go on the source side, it's even faster. So the response is very fast, and that's why having shown this, now what we are doing is packaging it in the form of a payload for ISRO's second unmanned human space flight, the testing phase of Gaganyaan, and we are going to fly this. And what we have promised there is we are going to show them dissipation up to 100 watts per centimeter square from a hot spot, in this case less than 1 centimeter square, and show it all of this within this 3 millimeter gap within 15 degrees centigrade temperature, so that the application that I talked about, that loop heat pipe, hot spots, all of those can be handled. So this is the first part that we have done, and basically what we have shown is that there is more to surfactants than just the reduction in surface tension. Primarily their foaming tendency, bubble repulsion, is a very useful property that can be used in innovative ways in your heat transfer applications. While at times that same foaming is detrimental to critical heat flux when you are doing heat transfer in upward gravity conditions, but in certain conditions where you can suitably manipulate the bubbles, confined spaces, adverse gravity conditions, that can be very useful. And you can imagine, yesterday we had talks on BTMS, and there was a talk of how you can have non-uniform thermal fluxes. Now you can have this envelope, very thin gap all around, and what this simply does is takes the same heat and distributes it evenly on the other side. So in many ways, we are also looking at the possibilities of using this for battery thermal management, load in terms to handle non-uniform loads and make it uniform loads for conventional heat sinks that we have. So that's the first part of the application. We have some papers on this if you want to read, both regarding the device development and the fundamental science of this bubble departure against gravity. So that's the first part of my talk. Now I am going to stick to boiling, but considering these interfaces and these bubbles are so interesting, and during my PhD I was doing a lot of boiling experiments, and whenever I used to do open chamber experiments, even though I was not monitoring the experiment, I was very clear which boiling regime I was in. So when I started my career independently, I said, why can't we hear what bubbles speak and figure out which boiling regime, what heat transfer we are in? And you can imagine the applications are immense. I don't need to give the background to this audience, but this is the typical boiling curve. Ideally, we want to be here, but we are rarely there. We usually adopt a high factor of safety, and we operate in this regime where the heat transfer coefficients are not very high. And that's just because of the uncertainties associated with prediction of critical heat flux, heat transfer coefficient. And Arvind said, first thing is, boiling is stochastic in nature. Secondly, it's sensitive to so many parameters. There's a great work by Dan Preston's group at Rice. They have shown that just depending on how much organic contaminants you absorb from our ambient, you can see the scatter in critical heat flux for same type of experiments. Long ago, Mose et al. 2022, they just did a literature survey and found copper surface, water as the boiling fluid, and what is the critical heat flux value and the superheat. Look, practically speaking, if I am a reviewer, it's the same experiment, right? Look at the scatter in the data. Somewhere from 15 degree superheat to 40 degree superheat, people have reported, and these are published papers, okay? And the heat flux is 60 watts per centimeter square to maybe 180 watts per centimeter square. No special surface fabrication. So the point I am trying to make is, while many a times we are so much in behind accuracies, at times you have to recognize that boiling is a process like that. First of all, it's stochastic in nature, and secondly, during the course of experiments or the trials you are doing, things change. There are contaminations, there are depositions, many things we don't know. As we said, if I do an experiment and you do an experiment, exactly same thing, we may not get the same result. So the point is, then what's the answer? One of the answer is adopt factor of safeties of the order of magnitude 10. Great, but that limits how high we can dissipate. So what is the other thing? Do some sort of adaptive control. Why can't I know about the health of my boiling system and how far I am from this dangerous limit as my experiments are running? And that's what we want to do. And what this can do is, basically we are looking at slightly different sector, but that's also thermal management. If you look at the statistics regarding boiler failures around the world, they are staggering. And mind you, boilers have very strict code, okay? Not anybody can make a boiler and install it. But what is the issue? The issue is we do not really know the thermohydraulics. And secondly, even if we know with time how that changes, because all our calculations are based on day one. But eventually with time how those change, okay, we are not able to keep track of, because you can imagine how many thermal sensors and how many pressure sensors are you going to put in your system. So we want to address all of this, and we want to do this slightly, again focusing on the bubbles, which are very difficult to see inside a boiler. So how do we do this? So you can imagine a very classical boiler that we teach in our heat transfer courses, right? What's the issue? The issue is there are tubes. Inside tubes you are boiling and you don't want dry out. Issue is where dry out happens is not known to you. There are thousands of tubes. You cannot put thermocouples everywhere, right? So thermal characterization is not possible. While all of us love high-speed cameras, and no offense, I myself have a lot of them, right? The point is we can do these for visualization, but in real industrial applications we don't have that freedom. There is a opaque, rigid, strong wall. We cannot see what's happening inside, right? So that's also gone. So what can we do? All of these bubbles flowing still emit a sound. And the beauty of the sound is, if you have a large boiling chamber, you put one sensor, it's getting the sound of all of these bubbles. So it's much more global in terms of the kind of measurements it does. Spatiotemporal resolution is very high. So we want to do that. We want to hear the sound of bubbles during boiling. The point is, we are not new. One second, I didn't check this, just give me 1 second. There's some sound playing in the background. And so this is the sound of sea waves. You know why there's this sea sound? If you go deep inside the sea, there is hardly any sound. The sound is due to this churning that we have on the shore and the bubbles that we create, the foams that we create. Why is it milky white? Because it's bubbles, right? So they emit sound everywhere, okay? Whether it's propellers, cavitation problem, everything is this sound, right? And there's a very famous relation by Minard, who studied the air bubbles and said that the fundamental frequency of the sound of bubbles is basically inversely proportional to the size of the bubbles. So you have smaller bubbles, they give you higher pitch sound. And this is very well known. However, it is known for air bubbles, right? So there is a lot of talk about sound of bubbles. In fact, Westwater, okay, way back in 1955 published this great article in Science where they said, you know what, heat flux versus decibel level, or the magnitude or in the intensity of the sound has a relation, something very similar to the boiling curve. And all of us know, boiling starts, there is sound, goes to critical heat flux, more sound, suddenly drops down as soon as we go into film boiling regime. But after that, some people attempted, but this line of thought of research was left because people realized boiling sound is nothing more than noise. They termed it as white noise. And for those of you not familiar, white noise is something which doesn't have any distinct frequency feature. It has emissions throughout the whole spectrum, so you cannot make a pattern saying that primarily this is my frequency. And it is understood because boiling has so many sources for emitting sound. There's a nucleation process which gives you sound, if it's subcooled fluid, cavitation, surface popping, that gives you a sound. Oscillations of all of these bubbles gives you sound. And now you can imagine how complex it is. One bubble is oscillating, emitting sound, that will further oscillate the second bubble, which will emit this sound, and there's coupling, right? So it's not very easy. So obviously because of that, the sound that all of us heard in 60s, 70s was noisy. We didn't have great sensors. Signal processing techniques were not that advanced. Computers were, the computational power was just coming up. So probably this field died. So when we started, we said again, let's use the same setup that I have shown you earlier. Everything is same. Only thing is we are going to add a hydrophone here. What is a hydrophone? In simple words, it's a microphone which will work properly inside water. And we take that and there is some signal processing, and basically what we are monitoring, intensity versus time plot, and then we are going to do all sorts of analysis that we know, Fourier transform and all of this during the boiling process. Here is a sample experiment. So what you see here is the acoustic intensity, intensity of sound. If you zoom in, you'll have a lot of these fluctuations with time, and during this time what we are doing in terms of heat transfer experiments, we are, if you see the heat flux on the primary y-axis and temperature on the secondary y-axis, we are ramping the heat flux in our boiling experiments until we get to critical heat flux. So this here is the nucleate boiling regime, and at critical heat flux goes down, temperature shoots up. This is where we shut off the power to our heater, and then basically it cools down. Okay, and if you have seen the boiling curve, you come back to the nucleate boiling curve and you cool down 5 minutes. Yes. So we do this, and at any instant nucleate boiling regime or other regimes, we take the acoustic data, do the FFT, you get different frequency spectrums. They seem to be changing as we get to the critical heat flux, and all of that information is finally put into this, which is called a spectrogram. So what you see on the x-axis is the time information, on the y-axis is the frequency information, and the color that you see represents at that time and at that frequency what's the intensity at that particular frequency. So all of this information is there, and this is sound. We also have the thermal data, visual data. We look at all of them together. So here I am just focusing on the critical heat flux. If you zoom in, heat flux was high, thermal runaway, temperature shoots up, heat flux goes down. If you look at the sound, there is some shift in frequency. So I am going to play this video. You will also hear the sound. All of the numbers are written there: heat flux, surface temperature, time. Just before critical heat flux. We are approaching critical heat flux. And this is where we have hit the critical heat flux. The point is, this can happen at any heat flux depending on what is your surface, how much is the contamination. But the shift in this behavior of the sound that you see, that the frequency components remains similar. We have tested it on various conditions. So we want to use this to basically have an in situ prediction of the health of my boiling unit, telling that now you are in DNB, become careful, instead of relying on correlations. So this coincided with the time, March 2020. All of us know what happened. All the experiments stopped, lab was shut down. So my student was also very upset. He couldn't do these great experiments. So he said, I want to do machine learning. And he came up with this slide to me, saying that, you know, how do they recognize crowd when there's huge gathering? So one of the things is to simply put a camera and see how many people are there, have pattern recognition, but the accuracies are improved if you have a few microphones there, because sound and visual images are much more accurate. I want to do this. I am looking at bubbles, but I want to hear their sound, and the way they use machine learning tools, I am going to use machine learning tools to predict what is happening with our system. And we picked up a very simple code from MATLAB. This is a tutorial, nothing special, which is a speech command recognition tool inbuilt in MATLAB. What it does is, you say yes, 10 people will say yes, it will store that sound and convert that to spectrogram. No, and similarly it will build a dictionary of all those keywords that you have. Then it will train a convolutional neural network. And then now, if you have somebody else saying yes, it will say, oh, this person is saying yes. So it's speech command recognition. So there are classes. For those classes you have training, and then you have prediction. And he said, my classes are no sound, background, silent. Nucleate boiling, I'll put all of the sound of the nucleate boiling in one class. Departure from nucleate boiling or pre-CHF as the second class. And then transition boiling as the third class. And without getting any information regarding the heat transfer, I want to predict all of the boiling regimes. And here is the result. What you see here, these colors are the prediction of the regimes. Yellow means right now we are in the nucleate boiling. And as we are getting close to the critical heat flux, the prediction tool itself says, oh, you are near the critical heat flux, and then transition boiling and all of that. So we had very accurate prediction of the various regimes, which we decipher from the boiling curves without getting any information from the thermal data. And this we did in various types of solutions and surfaces. And what was very important, just last slide, what was very important, he used this to show that now you can have an adaptive control. So here is a typical boiling curve. This is the critical heat flux. If you know, if you give a heat flux beyond this, you will have thermal runaway. He said, since I know that now I am near critical heat flux, I will have a jet turning on. So I am going to give a heat flux which is varying in cyclic manner and above the CHF, but my code will automatically detect when I am near CHF, turn on this simple jet, not a complicated setup, and operate in this high heat flux regime. And look at the result. We are getting to critical heat flux, we get above the critical heat flux, jet basically kills that big bubble. The temperature comes down, again the bubbles start. So the point is, this is adaptive control. So the system doesn't really care what heat flux you are at, what correlations you are using in. If it hears that this bubble is now getting to boiling crisis, I am going to kick in the safety mechanism. So this is what we are going to pursue further. Actually, we are doing some CFD simulations to predict all of this bubble dynamics using CFD, because in CFD you also have pressure signal, and pressure is nothing but acoustics. But I will end here. Thanks a lot for your attention, and I am open to any questions.
So thank you, Rishi, for a very interesting talk. And any quick questions? We'll take maybe 2 or 3 questions.
So I realized the first part of your talk was about microgravity, but it seems to me that you've solved the much more challenging problem of heat transfer in hypergravity, and you didn't mention that.
Means, yes, that's true. Even in hypergravity, confined spaces, primarily I would say in confined spaces. Yeah, the biggest challenges with you are saying higher gravity? Yeah. As a
that's much more challenging than microgravity, and that's what you've done. So you can go into
do you mean adverse gravity or hypergravity?
hypergravity, so like 2, 3, 4 G.
Yes.
You go into a centrifuge, that's much more difficult.
Yes, in terms of yes, if you are talking about bubble behavior, yes, this can also handle that. I never thought about that, but that's true. Yeah, yeah,
that's the more interesting part of what you presented.
yeah, that's interesting. I'll talk to you regarding that. Thank you.
Thank you for it. It was really an excellent presentation. I really enjoyed it. Why do you need the filling factor 1? I mean, you said that you have this one with the 1, and it's working. It seems that it's working, but why so high? I mean, 0.9 is not enough?
So the problem is, if you want to operate this at any orientation, okay, you cannot afford air gaps or vapor gaps, okay. So we simply make it 1, and then we have a small bellows which can take care of the pressure, okay, because you cannot have it completely filled.
This was in fact my second question. Okay.
So we have a very small bellows,
because you need to have something like
we have a small bellows,
okay.
but it's all integrated, one time sealed. There is nothing regarding it. Yes.
Because I was thinking, if you put 0.9, you have this kind of bellow inside.
But you cannot do that, because if you go to a particular orientation where the
Then
bubble
of
gets
course,
stuck
yes.
there, then everything is.
Even if there is a lot of mixing and so on.
Even if, but right at the startup, you can have bubbles right sitting on the heater, and there is this thermal runaway.
Yeah, maybe I'll just.
Hello. It was really very nice talk and covering all the aspects regarding the acoustic features of this bubble dynamics. My question lies in the understanding of you worked with the static dynamics of the bubble. It's a static bubble dynamics. Suppose you have the flow boiling in microchannels or confined spaces. How do you correlate your work with that sense, and what is the futuristic aspects to be extended based on your work?
Almost nothing changes. The sound of flow just by itself is not much. The sound in flow boiling will be the sound due to these bubbles, right? So obviously we plan to do that. You can basically extend this, right? And fundamentally looking at all of the sound emissions, the fundamental properties we have been talking about bubbles, right? One of the interesting things is, and I had a slide later, but I ended it here because we are running out of time. The sound of the bubbles is dependent on its volume, not really the shape. So what changes in flow boiling is, because of this flow, these bubbles are no more axisymmetric or whatever, but roughly if you know what are the sizes and other things, you can very well predict the sound of even flow boiling. So we are going in that direction.
So don't you think that just putting the hydrophone inside this water, that is going to be the damped of your sounds, But suppose you are working with the flow boiling in microchannels, you cannot keep the sound.
But you always have an
into it.
inlet manifold.
That seems because your boiling is somewhere away from this inlet
But
manifold.
as I said, the sound propagates. Okay, if there are lobbies in a hostel and you are standing here, as long as all of that information gets picked up, and these days these acoustic sensors are very well advanced and the filtering techniques are great, so you can really tell which sound is coming from which source. So again, I am also hypothesizing, but I think it will be much easier than what we think.
Yeah, see, in your work, because of these zero gravity problems, yeah, you have replicated the zero gravity, and you are pushing the small nucleations below, and you are getting some bubbles to be detached from the surface. So it's a kind of static phenomena, but that is not a case of when you are going with the dynamic phenomena, where you are working with the two kind of contact angles. So wherein
Dynamic
when it is
means what you are talking about, flow.
yeah, it's a bubble is moving, no? Because the bubble
There's a
has to
flow.
move with this.
See, if there is flow in zero gravity also, once there is flow, there is a very good work by Mudawar. If there is flow and the mass flux levels are above a limit, you really don't need gravity. So we are anyways not talking about active systems. You can afford active systems in zero gravity. We have the solution. Whatever solution works here on Earth works in space. We are talking about not having active systems, completely passive system. That's when this can be useful.
Yeah, even in passive systems there is a flow. Like suppose you are going with the pulsating heat pipe, there is a kind of two-phase flow being incorporated.
So
into
again,
it.
don't think of putting these in heat pipes, because now too much foam pushing the bubbles when there are too much foams is much more difficult. The drag is higher, so it's not going to, this concept is not going to work in heat pipes. People have tried putting these foaming solutions in heat pipes. It doesn't work actually. You will not be able to push the foam out.
Yeah.
Thank you.